Once upon a time, sharing video meant digging a small suitcase out of the closet and arming yourself with a shoulder-mounted camcorder, and hoping the batteries weren't dead. They always were. Then, if you managed to actually capture the moment and wanted to share it in all of its grainy glory, you had to figure out how to duplicate a VHS. Now anyone can pull out their smartphone and start live streaming to the world. Rob Green is here to talk about the modern marvel of video streaming and what Xilinx is doing to make it even better. Welcome to Tech Chats, Rob.
Hi, thanks, Chris. Nice to be here.
It's great to have you. Now, let's just start off with what's happening with video streaming right now.
Well, so streaming video is becoming ever more popular. I think the global pandemics we've seen this year have really only accelerated the deployment of remote streaming applications because professionals are kind of forced to produce and contribute media content from their homes. But I think even before all of that, there was already a growing trend to stream more content. So that means deploying more streaming endpoints and high-performance codecs everywhere to get more live events into consumers' devices and into the TV sets. But streaming's not without its challenges, and today I want to walk through some of the major issues and choices that are being faced by streaming equipment developers. First and foremost, live IP streaming is definitely on the rise. So that's driven by major services such as YouTube and Facebook, who now offer live services. We're also seeing the rise of esports services such as Twitch, YouTube Gaming, and Hitbox. It's created this whole new breed of broadcasters. So they stream thousands of simultaneous gaming feeds to their viewers, and all of them need encoding and then transcoding to convert all these feeds to different formats, resolutions, and bit rates. Another big trend, of course, is the growth of 4K video. However, for live IP streaming, 4K actually presents a major challenge because you've got constrained bandwidth of the content delivery pipes. But I think the growing ubiquity of 4K capable cameras and smartphones on the acquisition side, it kind of makes sense to deliver a 4K stream to the transcoder while you stream one or more scaled or cropped versions of that same feed at the outbound side. And bear in mind, if you transcode a 4K HEVC feed to several output formats, you require about 5 times the processing power of H.264 encoding. And then finally is the growing effort that is going on to reduce the end-to-end latency of live streams. So how do these trends affect your product requirements? So there are certain things like analytics, which is being used in OTT or internet delivery. And how does OTT delivery surpass and enhance the broadcast user experience? Well, we think that analytics will play a key role in that. And they all tie into the overall goal of implementing and continually improving on a high quality of experience for the end user. In terms of multi-stream and multi-codecs, well, H.264 is ubiquitous in the compression world, but the next generation of advanced compression is available with H.265 or HEVC. There are other codecs, of course, but the ability to use one or both of these codecs is really a requirement for a flexible transcoding solution, along with the ability to encode the same source content at different bit rates and resolutions simultaneously. In terms of performance requirements, there's a need for portable solutions as measured by SWaP, or size, weight, and power. So integrating a hardened encode-decode core enables dramatic power, size, and weight reductions. And then finally, we have the requirement to adapt to different network and content conditions. So this requires an intelligent solution that can be reprogrammed and repurposed on demand.
You mentioned some different conditions and use cases. So how do those different use cases influence design requirements?
It's a good question. So, straight away in the previous slide, we talked about the flexibility to support different video formats, different numbers of streams, and so on. But you also need to be flexible in your streaming codec implementations. So to highlight the different parameters and trade-offs that are required in codecs, we can take a look at some example applications that are mapped to kind of a radar graph. Things like video quality, compression, cost, latency, and power, and see how those trade-offs apply depending on the use case. So the first one is a broadcast distribution encoder. And the main requirements for this kind of encoder are the highest video quality at the bandwidth that's available, which can be between 2 and 6 megabits per second, for instance. And the encoders are selected by broadcasters primarily on video quality shootouts between those vendors of the encoders. And that means that cost, latency, and power can be sacrificed somewhat to get the best quality. Now, if we compare that with a camera back transmitter or a wireless video encoder at a live sports event, the wireless bitrate that's available is also limited. So the video quality, although it's important, can be sacrificed to some extent to stay within those bandwidth limits. But in a camera back application, cost, power, and particularly latency, because no one wants delays in any sports coverage, they become much more important than a distribution encoder. The next example is video conferencing. So if you've got two-way communication, you'll typically have much lower bandwidth, so your compression needs need to be a lot greater. And video quality can be sacrificed to really reduce the bit rate down. But latency is critical. Conferencing, and particularly for consumers, needs to have very low delay for conversations, but it also has to have much lower cost structures generally because it's more of a consumer kind of market. And then finally, we've got live streaming. So this is kind of an encoder box where you've got delivery over YouTube Live or Facebook Live. And here you can sacrifice a lot of video quality for the bandwidth, and cost is much more of a decision factor. Latency can be sacrificed to some extent, but it needs to be low if you're covering live events or sports, lower sports tiers, for example. So the upshot is, if you look at all of these different trade-offs that can be made, there isn't really one codec that fits all the use cases. What you really need is a codec that has as much flexibility as possible to cover as much of the requirements radar graph as possible.
You brought up flexibility multiple times, and of course, Xilinx offers a lot of flexibility with FPGAs. So what do you have that addresses the live streaming market?
Yeah, so you could buy an off-the-shelf standard product codec. So you could buy or make an ASIC or an ASSP, but really it's unlikely to match your exact needs, or it'll have a significant drawback that makes it less ideal for your application. So for instance, you could get the best video quality, but its latency would be too much, or the latency would be perfect, but the power of the device is way too high. So what you need is a flexible approach where you can really fine-tune your implementation to meet your application needs and make less trade-offs than you would with a standard codec product offering off the shelf. So this is where we introduced the Zinc UltraScale Plus MPSoC from Xilinx. And this is a multi-processor SoC built on a common real-time processor and programmable logic equipped platform. And we've got three distinct variants of the device. And the ones that are ideal for streaming and that we'll focus on today are the video codec devices, or the EV family. So if you look at the Zinc UltraScale Plus MPSoC, it's a heterogeneous SoC that comprises of many different processing engines and a long list of high-speed peripherals. It's got advanced I/O capabilities, and it's got programmable logic. Of particular interest for streaming applications, as I mentioned, our EV variant includes a hardened video codec unit, or VCU. And this is a hardened block which is physically located within the programmable logic part of the device to offer maximum flexibility and still harden the key encode-decode functionality to reduce its size, to reduce its power consumption, and so forth. Now, we support a number of different codec profiles, where profiles are a mixture of encoding tools. We support baseline, main, and high profiles for AVC or H.264, and main intra for HEVC or H.265. Now, should you require greater than one stream of video, we can actually support up to 32 streams for encode and 32 streams for decode simultaneously and bidirectionally. As long as you don't exceed the raw input bitrate of 4K 60, we can handle multiple streams. We won't elaborate on all of the different encoding tools in this presentation due to time, but in summary, we can support both constant bitrate, variable bitrate, along with a full selection of different GOP structures, iframes, P-frames, and B-frames, etc. And it's all been designed with UHD 4K video in mind. So they're really ideal devices for multimedia applications, not just in Pro AV and broadcast, but areas such as automotive driver assistance systems, surveillance applications, and a whole host of other embedded vision applications. So having this programmability in both the hardware and software domains on the same SoC provides a lot of flexibility and scalability in terms of any-to-any high-speed video and audio interfaces, and differentiation is still available to enable customized image and video processing for different multimedia pipelines. Now, Clearly, this shows we've hardened a really flexible and capable video codec implementation, and I think that will certainly adapt to all kinds of streaming needs. So let's take a look at what a typical streaming video pipeline would look on a Zinc UltraScale Plus MPSoC EV device. So we have in the top left corner a quad-core APU, which is a part of a PS or processing system. It's really the heart of the MPSoC solution, and it hosts the system runtime software stack, which includes things like the operating system, normally Linux, the management layers, the media software stack, and things like audio processing can be done in the software domain, along with any of your value-added software applications. Then we show the video pipeline at the bottom of the architecture in the programmable logic domain. And the PL or programmable logic is used to host things like video connectivity I/O, the video processing pipeline, any soft video codecs, and maybe some additional Ethernet interfaces if needed. And as we said earlier, the VCU or the video codec unit is a hardened block within that programmable logic domain. So the combination of this programmable logic and a hardened codec engine, this is where you get an ideal trade-off between flexibility, power consumption, and latency, and it's all done in real time. The VCU enhances the solution by not taking up lots of valuable programmable logic resource to implement the high-quality codec. We've got integrated interfaces in the PS, so things like USB 3 and SD card interfaces, which are available if you want to do some storage solutions. But generally, the device is all programmable. It's programmable right across the hardware and software domains. So it offers unrivaled flexibility that the system designer can then choose where your processes and algorithms are handled to meet different performance and cost needs.
Anytime you have something really flexible like what you're showing here, you often have to deal with a lot of complexity as well. So what do you have to help keep things manageable?
Yeah, so codec systems are arguably one of the most complex systems you can build. So fortunately, Xilinx provides a whole comprehensive set of reference designs to support the VCU and to capture, process, and output multiple video streams. So the pipelines that we have work with external frame buffers in DDR memory under the control of an APU, an ARM processor unit, in the processing subsystem on the MPSoC device. And if we look at the reference designs that we provide on the Xilinx wiki pages, starting with the input pipelines, we have different options to support SDI, HDMI, MIPI camera inputs, internal test pattern generators, I2S audio, 10 gig Ethernet streams, and file storage on SATA, USB, or SD card. And that's all the different options in the capture side. For the processing pipelines, this is really where the encoding and the decoding happens. So as well as the VCU hardened IP, we have supporting IP that can perform high performance memory control and other codec features that we'll talk about later. And then finally, on the output side, we provide the output pipeline options such as HDMI display, SDI outputs, and 10 gigabit Ethernet streaming outputs. And as I say, all of these reference designs are available on the Xilinx wiki pages. The link is there. And they're really an ideal starting point to either just get familiar with the Zinc UltraScale Plus codec and all of its capabilities, or it can be a very good starting point for your own streaming developments. It's a complex system, but although it's complex, we've adopted a lot of commonly used multimedia frameworks to abstract away from the hardware and make using the codec and supporting IP much easier, particularly for streaming applications. So the reference designs all use embedded Peta Linux, which is a Xilinx package Linux offering, and all that runs on the ARM cores in the MPSoC. And as such, the control of all the codec and video IP parameters can be done through simple GStreamer commands, either on a command line or through API calls from your own application. And really leveraging the open GStreamer framework means that you can benefit from all the plugins and tools that are developed by the community, not by Xilinx, but by video professionals in the global community to handle and control the capture, processing, and output pipelines that we mentioned in the last slide. You can use GStreamer to work with V4L2 input drivers. We can work with ALSA audio drivers, and we can also use KMS or DRM output drivers to tailor all of the AV pipelines from input through the codec to the output, all running in hardware to suit your specific use case. And that could be anything from setting up video formats to telling the codec to output at a constant bit rate or certain video quality characteristics, for example.
You mentioned that you're leveraging some open tools and the benefits that users get from that, but it also looks like you've all been pretty busy developing the codec itself.
Extremely busy, yeah. It's been a busy 2 or 3 years of building up a software stack to run on the hardware, and it's been built in both standard feature sets, but also on customer requirements as we've gone over the years. So our codec is really feature rich, and the feature set's grown considerably over the last couple of years to include a variety of functions, from handling more streams to supporting different GOP structures and improving the latency performance. And the choice of features really depends on the application that the codec is being used in. So having a software stack and all of these features really plays a vital role in navigating those trade-offs that we've discussed so far. So if you take mobile wireless video systems for live sports, for example, and we touched on that earlier, you will need very low latency and probably have very limited bandwidth. So some of the features that we could look at in our tool set are things like dynamic resolution change and encoder frame skip, which will continually trade off video quality to keep within your bitrate targets. We could also use slice-based encoding and decoding to reduce the end-to-end latency to under 30 milliseconds in our case, which is perfect for live environments. And we could also look at ROI, or region of interest encoding, in conjunction with machine learning. So we could detect faces and apply more bits and therefore more video quality to the areas your eyes are drawn to, i.e. the face, and then reduce bits in the much larger background area. That dramatically reduces your overall bit rate without really perceived quality loss. So the features, the performance, and the flexibility that's provided by our codec solution, I think, are unmatched by any other codec device.
You call out here your latency being under 30 milliseconds, which was important to most of the applications we talked about at the beginning. So can you talk a bit more about latency?
Yeah, as we saw earlier, I think latency requirements differ very much depending on the application and the use case. For many live environments, latency is really important, and it needs to be as low as possible. So things like sports, live events, news capture, all of these need really low latency. But actually 30 milliseconds is market leading. And we have, as I said, a flexible codec solution, which is based on programmable software and hardware. So we can optimize the capture and display pipelines, as well as add different features and functionality to the codec pipeline to reduce the latency considerably. So as I said, we actually provide the industry's lowest latency professional codec solution for H.264 and 265 with end-to-end latency. So that's capture, encode, decode, and display of less than 30 milliseconds. We also have low power capabilities as well. I think FPGAs and programmable devices are often perceived to be very high power devices. But if you look at the measurements that we've taken and which we provide for a full 4K 60 pipeline, so where you've got an HDMI input, you encode the stream, you decode it, and you display it output on an HDMI monitor. This only takes about 8.5 watts for the entire device. So it's pretty low given that you've got all that flexibility in place still. And that's very important for battery-powered applications such as wireless cameras and reducing the burden and cost associated with difficult thermal management in any application.
Okay, so if someone wants to get started with this Zynq UltraScale Plus MPSoC EV platform, where should they start?
We have a reference design, which I talked about earlier on the Xilinx wiki pages. That would be the first place to go and have a look at those designs and all the documentation that goes with it. But we do have some specific companion pieces which are very useful to learn about the complexities of these AV systems. Right? And anybody that's worked with video knows that AV systems are complex. So we provide comprehensive documentation and training to help with the implementation in any application in any market that would use these codecs. So we have on-demand training available in the Xilinx customer training portal, where you can learn how to build and run complex multimedia application using the Zynq UltraScale Plus MPSoC device, and also how to use the GStream framework. And there's over 16 hours of content, 4 hands-on labs to experiment with on the ZCU 106 multimedia platform. We also have PG252, so this is a comprehensive product guide and document of all of the VCU features and capabilities, and lots more information on how to design with the core and how to do application software development. And then a newer document that was released recently was UG 1449. And this is a user guide which really helps accelerate the integration of the VCU into customers' pipelines. So it will show you how to get started with multimedia IP, how to build video pipelines, how to set up GStreamer, how to debug things, that's important, and also guidelines for common use cases that we've seen so far. Along with that, we've also got the ZCU 106 multimedia and connectivity platform I mentioned briefly a second ago. So most of our reference design development is done on this platform. And the ZCU 106 is very powerful and capable. It's designed for high performance professional video processing, both in development and some deployment as well. And the onboard ZU7 EV device is surrounded by multiple interfaces, multiple AV interfaces such as HDMI, SDI and DisplayPort, Ethernet, USB, and loads more. And you've even got expansion slots for FMC cards so you can add more capabilities. So the ZCU 106 board is available now from Mouser Electronics. And there are other EV platforms available as well. So there's a range of devices and hardware available. But the ZCU 106 is perhaps the one that has the most capabilities and the one that we use for most professional deployments. So streaming is more popular than ever. As we've seen, there are many technical challenges and trade-offs that need to be made, and very much depending on your application and your use case. But hopefully this short introduction has shown that the Xilinx Zinc UltraScale Plus MPSoC is the ultimate streaming codec device. It offers full flexibility with both programmable software and hardware, and it offers the best balance of trade-offs that you can make for all kinds of streaming applications. You've got configurable bit rates, you've got video quality considerations, we've got market-leading low latency options, we've got a low power capability, and can be a cost-effective implementation as well. The codec comes with comprehensive reference designs that we talked about, and these will provide a really good starting point for your own designs. And we've adopted open and community-driven media frameworks like GStreamer to provide easy access to and control of these otherwise complex system parameters.
Thanks, Rob. Once again, that's Rob Green from Xilinx. If you'd like to learn more about the Xilinx Zinc UltraScale Plus MPSoC EV or the ZCU 106 multimedia and connectivity platform, click the links in the description or visit Mouser.com. And be sure to check back soon for the next episode of Tech Chats.